Good evening, everyone. My name is Amit. Am I audible?
Yes, sir.
Okay. So this is the 12th and
Good
final.
evening, sir.
Good evening, Pratik. This is the 12th and final session for live sessions for gate physics. Um, since I'll wait for a couple more minutes and so that other people may join. And the agenda for today is I have one question from small signal analysis of BJT, bipolar junction transistors, and after that we'll talk about field effect transistors. What are they? And in particular, junction field effect transistors, which are one of the simplest field effect transistors. Thereafter, I think in last class, I forget, someone asked me to talk a bit about digital to analog converters. We had solved questions for analog to digital converters, but we had not touched in detail about digital to analog converters. So I have incorporated one discussion over that also. That's that. And if you have any other doubts, you can feel free to flag them, to ask them right now, or sometime in between questions also. As always, I'll be explaining, starting with the questions, then explaining the concepts, then summarizing the question. And if you have any doubts, feel free to stop me anytime. Drop me an email anytime if you wish to. So that's that. Let's wait for 1 or 2 more minutes and then we'll start. Thank you. Are you able to see my screen now? Hi, good evening. Are you able to see my screen?
Yes, sir.
Okay, so we'll be starting right now. If other people join, I'll try to repeat myself. So let's begin. 1 second. Yeah, okay. So this is week 12, the final session for gate physics live sessions where we'll solve questions. My name is Amit, and today we'll start away with one question from small signal analysis of BJT. Remember that in last class we had talked about DC analysis of BJT, and today we are going to talk about small signal analysis. So I have already recorded this question. I'm going to play it now. So if you feel any problems regarding audio, video, or anything in general, just please raise your voice and I'll stop. So let me just play the video now. The problem statement from Gate Physics 2017 reads as follows. For the transistor amplifier circuit shown below, with R1 equal to 10 kilo ohms, R2 equal to 10 kilo ohms, and R3 equal to 10 kilo ohms, and beta equal to 99. Neglecting the emitter diode resistance, the input impedance of the amplifier looking into the base for the AC small signal is dash kilo ohms. This is a numerical answer type question and we need to find our answer and then round it off to 2 decimal places, and we'll fill in the blank here. The video is clear, audio as well as the visual. Is it clear? Please respond.
Yes, sir.
Okay. I'll continue now. So just getting right to the problem. So this is the BJT that's given to us. It's an NPN BJT, and it says that it's an amplifier circuit. And for this, we have to perform the AC analysis. So how do we go about doing it is that we first need to understand what is the model of a BJT as far as small signal analysis is concerned. So this is the BJT that we have, NPN BJT with collector, base and emitter. The current will flow out of the emitter, DC in DC analysis. So this is the conversion, this is the model that we use that for the small signal analysis. So you can see that the base terminal is over here on the left, the collector is on the right, which is on the top over here, and emitter is at the bottom as always. Now in the question it was given that we can neglect the emitter diode resistance. This means that we can effectively ignore this resistance R pi here. So by ignoring, I mean we assume that this to be 0. So effectively our BJT for small signal analysis can be converted to this. We have assumed R pi equal to 0. So this is the circuit that we finally get. Now what I'll do is that I'll plug in wherever BJT is used. I'll plug in these circuit elements. So everything is a wire except for this dependent current source, because this is a current source as indicated by this arrow. It's dependent. This is dependent on the IB, where beta is the current gain of this transistor, DC current gain of this transistor. Now this was the circuit given to us. So what I'll do, I'll simply replace this BJT with, I'll plug the BJT model that we have developed over here. So I've just done that. So in removing this, so it's R1, R2, VCC, V in all remain the same. R3 also remains the same, and the V out, the port remains the same. Just that base, collector and emitter have been replaced with this. So so now moving forward, this is after we got this result after the first step. Now the second step is to remove all the independent DC sources. Now remember, I'll point out independent DC sources. So what are the independent DC sources that we have here? So first independent DC source that we have here is this VCC. It's an independent DC source, DC voltage source. So we'll put VCC to ground. By removing, we mean all the independent voltage sources should be grounded, and all independent current sources to be open circuit. So all dependent current source to be open circuit. Now note that this is not an independent current source. This is a dependent current source. See this term here. So this will not be open circuited, right? But VCC, similarly, V in is a dependent, is an independent voltage source, DC voltage source. So this will also, we can also ground this, right? So what we'll get something like this. So see, VCC is grounded, right? So if we ground VCC like
Excuse me for a minute. Someone is trying to join. I'll replay the video from here.
So if we ground VCC like this, so so see, VCC is grounded, right? So if we ground VCC like this, so what I've done here is that, so R2 remains the same here, this circuit remains the same. So R1 is between the base, which is this node here, and the ground. VCC is ground. So I've just rather than this leg should be up, I just put it down. Nothing has changed. So everything remains the same. Similarly, this collector will now be grounded because VCC has been grounded. So this remains the same. So this is the circuit that we have gotten. So I'll reiterate that remove independent DC sources means all independent voltage sources to be grounded, just like VCC, and all independent current sources to be open circuited. There are no independent current sources. This is a dependent current source. So nothing will change over here. Now, this is the circuit that we had. Now in the third step, we'll put a test source. So where we had to find the input impedance. So what we'll do at the base, so this is the base, we'll put a test source. So this is the V test, this is the I test. So we have put a test voltage source, and we'll measure the test current, and we can simply define the input impedance is nothing but V test over I test. So whatever current we are pushing in the denominator, and in the numerator we have the voltage, the AC voltage, small signal AC voltage that we are applying. In the denominator. So what the analysis over here is, this is a very common feature for AC analysis. So wherever you want to find the impedance, you put a test source over there and you feed in and you try to measure the current, and you divide the two and you get the input impedance. So for instance, if we were required output impedance, we would have put a test source over here at the collector, and we have measured the test source. But since we are talking about the input impedance from base, question explicitly asked, hence we are putting a test source at the base, and we'll simply measure the test current, and we'll obtain the input impedance using this very simple formula. And in the numerator we have the voltage, the AC voltage, small signal AC voltage that we are applying. Now, so this is the final the circuit diagram that we have over here, and these are the constants that were given to us in the problem itself. What we need to find is the input impedance, which is defined at V test over I test. So we'll start with that, and let's just first define a couple of currents which I've defined here. I1 is the current flowing through the resistor R1, I2 is the current flowing through the resistor that we have here R2. Now what I'll do is that, so we'll look carefully and look at this node, the emitter node over here. So this voltage is nothing but V test, right? This is nothing but V test, and this is just a wire. So all the voltages here will be V test. Similarly, this will also be, let's call this for the time being VE. Now, first what I'll do is KCL. I'll apply KCL at voltage at node VE. So incoming current is nothing but this IB and IC, right? So I'll write it as IB plus IC is equal to IE. So I'll get IE equal to simply beta plus 1. This is what I'll get, and what I'll do if I apply Ohm's law across this resistor, right? So I'll write this as well. So I'll write Ohm's law across R3. So I'll write that will be VE minus 0 is equal to IE times R3. And now I know the value of IE, and VE will be nothing but V test. Note that this is just a wire. This over here is just a wire. So VE will be nothing but V test. So I can write V test is equal to IE. The value of IE is nothing but beta plus 1 times IB times 3, right? So this is an expression that we have obtained, and from this I can write IB is equal to V test over beta plus 1 times R3, and let's call this expression 1. Now in step 3, what I'll do is I'll apply KCL at this node. Let's call this as Vin node. KCL at Vin. So we'll put all the incoming current. So incoming current is nothing but I test. So you see this is the incoming current in the blue that we see here. And the outgoing current is nothing but I1 plus I2 plus IB. So I'll write I1 plus I2 plus IB. So I'll get I test equal to, now I1 is nothing but, so we know that this voltage is nothing but V test. This is a wire. So this will come out to be V test over R1 plus V test over R2, and we know the value of IB from expression 1, which we'll use here. So that will be V test over beta plus 1 times R3, and from this I can get I test is equal to V test. This will be R1 parallel R2 parallel beta plus 1 times R3, and thus I'll get V test over I test. V test over I test will be nothing but, so sorry, this was V test over this. So V test over I test I will get is R1 parallel R2 parallel beta plus 1 R3. So this is 10k parallel 10k parallel. So beta is 99, so that will be 100 into R3, that will be 100k. So that will be, if we this 10k parallel 10k is 5k, so 5k parallel 100k. So let me just look into my calculator, and yeah, so this value is coming out to be 4.76 kilo ohms. So this is nothing but V test over I test, nothing but input impedance Zn, right? So we find out Zn equal to 4.76k. Now this is also known as Zn, input impedance. So we just found out that the input impedance is 4.76 kilo ohms, and this is already up to 2 decimal places. So that is all that we had to do.
So we are done with the first question. I'll reiterate that this was the problem given and we had to perform the small signal analysis. So which you can see here, that we had to perform the small signal analysis because this was given small AC signal. So we did that. We solved, if we followed a few steps, we obtained the model for this BJT small signal model. Then we removed all the independent sources like VCC over here, and then we simply put in a test source. We saw that we put in a test source and we finally solved the problem. This was, after that was nothing but KCL and KVL. That was fairly simple, but it's just that the steps are important, that the order is important, and you remove the independent sources, not the dependent sources. So we did all that and we obtained this result. So we are done with the first problem. If you have any comments, any questions, please go ahead and ask. I'll pause a bit here so that you're able to gather your thoughts. So any comments? If not, then we are completed with a discussion on BJT. Now next we'll be moving to field effect transistors. These are also, BJT is a type of transistors, bipolar junction transistor. Another type of junction transistor is field effect transistors, in particular junction field effect transistors, and in a bit we'll solve 2 or 3 of their problems. So if there are no further comments, then I'll go ahead and start solving that problem.
Statement from Gate Physics 2013 reads as follows. An N-channel junction field effect transistor has 5 milliamps source to drain current at shorted gate, also known as IDSS, and 5 volts pinch off voltage VP. Calculate the drain current in milliamps for a gate source voltage VGS of minus 2.5 volts. The answer should be up to 2 decimal places. This is a numerical answer type question, and we need to find the drain current for this problem in milliamps, and then we'll round off our answer to 2 decimal places as required and fill in the blank over here. Let's first try to understand what a junction field effect transistor is, also known in short as JFET. So on the left hand side, you can see the symbol for that is the N-type JFET. Why N-type? Because the conduction here is due to electrons. And on the right hand side, you can see the P-type JFETs. So you can see that this symbol, one vertical line and these 2 rectangular lines, and this the symbol inside the circle is for the NJFET, and if the arrow is pointing outwards from the gate, it's known as PJFET. It's a 3-terminal device, so you have the drain, you have the gate, and you have the source. These are the 3 terminals. And why it's a transistor? Because it's the gate that is controlling how much current flows between drain and source. So that's the definition of a transistor, when the 3rd terminal gate is controlling the current flow between the drain and source. And this is a junction field effect transistor. By that we mean that there are junctions in here. So you can see for NJFET you have an N-type substrate in which there are 2 P-type regions. These are the gates. So gate is P-type while drain and source are the N-type. So effectively the current flow will happen in this vertical region, the N-type region, hence this is NJFET. Similarly for P-type, you have the gate is N-type and the drain and source are P-type, and the conduction will be due to the holes for P JFET. For our discussion, we'll restrict ourselves to NJFET because the discussion remains the same. Just the current direction is reversed. The physics behind these devices remain the same. Right. So now you can see that so this is unbiased condition. So VGS is 0 and VDS is 0, which you can see over here. Now what we are doing here is that the gate is p type and the drain, this is the n type region. So naturally, even if there is no bias, there is a depletion layer which you can see in the dashed line here will form. So what happens if, let's say, we apply a slightly negative bias, reverse bias to gate source junction? So note that negative bias to gate source junction, this is p type, gate is p type. This means we apply some negative voltage, right? So we apply some negative voltage, so naturally we expect the depletion region to increase, because now the gate source and the gate drain also have become reverse bias. So you can see the depletion region has increased. Now what happens is that, let's increase so we have applied some gate voltage, let's say some minus 0.5, minus 1 volt. So below a certain threshold, which we call pinch off. What is pinch off? If we apply such a large reverse bias to gate source, right, that these two depletion regions which we are seeing here and here, if they touch each other, which you can see happening over here, right, here the two depletion regions are touching. So here now so even if you apply, let's say hypothetically, some drain source current, no current can flow. Drain source bias, no current can flow. Hence this condition is known as the pinch off condition, and the device will not conduct. So such a voltage at which the two depletion regions merge is known as the pinch off voltage. So this is a negative voltage, because note that we are applying a negative bias. So below this, the device cannot conduct. Now in order to completely understand the working, now we'll do the other case in which we'll keep VGS equal to 0, the gate source bias will remain 0, and we'll try to vary the drain source bias. So as usual, if no bias is applied, so the small depletion region will be formed here. Now let's apply some drain bias, some small drain bias. So what will happen is that, so gate drain will again become reverse bias. Note that drain is n type and gate is p type, and we are applying a positive voltage to drain. Gate is at 0, right? So this junction becomes reverse bias, and hence the depletion region has increased. So note that this channel has become a bit narrow, right? So electrons can still flow, but their flow will be kind of slightly restricted here, right? And but so since VDS is not so high that these two depletion regions have touched, so now let's increase the depletion, and you can see some current is flowing over here, right? Because now there is a bias VDS, so electrons can flow through this channel comfortably over here, right? Right. So now let's increase the drain bias even more to this. So what will happen is that these two depletion regions will almost touch, right? And even if you increase any drain bias for now, the current cannot increase, because they're almost touching. There's a very narrow gap, so all the traffic is flowing through a very narrow gap over here, right? And so even if you increase the drain bias over a certain point, which is coincidentally the same as the pinch off voltage that we saw for the gate, the drain current will not increase. So drain current will sort of saturate, and this we can express over here, right? So you can see that after a certain VDS, which is defined here as VP, the current is constant. Right? And below a threshold, in the orange region, below a certain VGS, right? So this is the VGS that we are talking about over here, in this VGS, in this level. Below this, there's no conduction, because it has been pinched off. The channel has been pinched off and no electrons can flow. So no current is flowing over here. And this region is the ohmic region. This is why it's called ohmic, because you see the vertical axis is current and the horizontal axis is voltage, and you see a linear relation. So I directly proportional to V. That's why this region is called the ohmic region. And after a very high drain voltage, the device breaks down, because note that this is the PN junction. And this is the equation that we encounter to solve for a given VGS and a given pinch off voltage. And obviously VDSS is when VGS is equal to 0, what is the current? So this is a good metric which is provided by in the data sheet. So this is also in the problems you will know this. So ID is IDSS times 1 minus VGS over VP whole square. So this is the formula which we use to arrive at the current in the saturation condition. Getting back to the problem, this was the NFET NJFET that was given to us. IDSS equal to 5 milliamps and pinch of voltage is -5. So I've just taken it small, it's 5 volts, and VGS is -2.5 volts. So you can clearly see that the VGS over here, right? So it is greater than VP, because no, VGS is -0.5 and VP is -5. So this means device will conduct, because it's not pinched off, right? Device will conduct. And what is the formula? So I have just denoted the currents over here. You can see Ig is 0. We neglect the gate current, so we assume that no, in the depletion region, no current is flowing through the gate, and consequently ID will be equal to Is, because if like KCL over here, so there's no current is flowing in, so ID will be equal to Is, and I have denoted VD, VG and Vs for just for the simplification, just so that we are able to understand where is drain and where is source. Right, and this is the formula that we'll use. We established that device will conduct. This is the formula we'll use. So we'll simply plug in the values. So IDSS is nothing but 5 milliamps times 1 minus, so minus VGS, this will be minus into minus 2.5 divided by minus of -5 whole square. So this will come out to be 5 milliamps times, so minus will become plus, so that will be 2.5 upon 5 whole square. So this will be 5 milliamps 1 minus half whole square. So that's 5 milliamps into 1 over 2 square. So that will be 5 milliamps over 4, which is nothing but 1.25 milliamps. So we see there is some finite current flowing over here. Note that it's not high as the IDSS, because IDSS is when VGS equal to 0, and we have still VGS as some negative voltage, right? So there will be some current flowing, which is 1.25 milliamps, and so we have obtained the current here in milliamps, which was required, and up to 2 decimal places. So the answer here would be 1.25. Thank you for listening. So we're done with the second problem for the day. This was the problem related to the junction field effect transistors. So these are very similar to what we had talked about, the bipolar junction transistors. So there it was the current that was controlling. Remember, it was the base current that was controlling the collector, the current flowing from emitter to collector. Here it's just that it's a voltage control device. So here the gate voltage is controlling that how much current will flow between the drain and the source, and we saw that this is formed due to the PN junctions, just like we saw that BJTs also had 2 PN junctions. One PN junction was between base and emitter, and the second PN junction was between base and collector. So those are the parallels, but this is FETs are slightly better because the gate current is usually very less. So we remember that we had assumed it to be almost equal to 0. So their base current was some finite, some microamps. Here the gate current in case of FETs is very low. It's a good FET will have something like tens or hundreds of nanoamps of current, so it's very low as compared to BJTs. So that's why FETs have become more popular. In fact, BJTs are very rarely used nowadays, especially in your consumer electronics. Right, so now that we have seen the concepts relating to the junction FETs. Now I'll go ahead and we'll solve one more problem. If you have any doubts, you can ask right now. If you want me to clarify some concept, I'll pause for a minute, and then if it's all good from your side, then we'll go ahead and see the next problem. So I'll just pause here. If you have any comments, any questions, please go ahead. All right, I'll start with the next question. That's question number 3 for today. This also relates to junction field effect transistors, and we'll see it right now. Let me share my screen. So you should be able to see my screen now. The problem statement from Gate Physics 2015 reads as follows. In the given circuit, the voltage across the source resistor is 1 volts. The drain voltage in volts is, we have been given a question which is JFET, junction field effect transistor, and with some resistors and some power supply, and we need to find what is the drain voltage. This is a numerical answer type question. we'll find our answer and fill in the blank over here. So getting back to the problem, this was the question given NJFET with Vs equal to 1 volts and we need to find the Vd. So first let's just label some nodes. So this is the current, Ig will be 0. We assume that no current is flowing through the gate, which is the reverse bias case here, and we assume the current to be 0. So consequently Id will be equal to Is, right? If you apply KCL, so I'll write KCL across NJFET. So what's the incoming current? Incoming current is Ig. The other incoming current is Id over here. This should be equal to outflowing current, which is Is. This, and since we have assumed Is to be 0, so simply Id will be equal to Is. So this is just a it's a very fair assumption to do this now. And now we'll also label the node. So Vs is been given equal to 1 volts. Vd we need to find out, and Vg is the node, is the gate voltage over here. Now, so in order to find Vd, if we find Id, that will do the trick. So how do we find Id? So simply, so let's apply. So this will be step 2. This was step 1, KCL across. So step 2 would be Ohm's law across the resistor Rs. So this is the Rs resistor, the source. This is also known as source resistor sometimes, right? So let's call this Rs. So we apply Ohm's law. I'll write Vs minus 0, V equal to IR. So this will be Is times Rs. So we know the value of Vs is 1 and Is we don't know. Rs we know is 500 ohms. So from this Is will come out to be, so if we, that's 1 over 500. So if we talk in milliamps, so this will be 2 milliamps. So Is we have obtained is 2 milliamps. This implies Id will also be 2 milliamps because Id is equal to Is. So this will also be 2 milliamps. So we obtain, note that Id equal to Is. Now the final step in this problem is we apply Ohm's law across this resistor. This is also sometimes called as the drain resistor because it's connected to the drain, and let's call this Rd. So step 3 is Ohm's law across Rd. So we'll write that. So it's 25 minus Vd. This is the voltage drop across Rd. You see 25 minus Vd equal to Id times Rd. Very simple. So now we'll write Vd is equal to, just rearranging some terms, it will be 25 minus Id Rd. That's 25 minus the value of Id we obtained is 2 milliamps times the value of Rd is 5 kilo ohms. So that will be 25 minus 10. So this will come out to be 15 volts. So Vd we have obtained as 15 volts, and this is the answer that we were required to find. So note that we were required to find the drain voltage. This is what we defined as the drain voltage in our problem. This was the source voltage. So we have obtained that the drain voltage for this specific circuit implementing an N-type junction field effect transistor is 15 volts. Okay, so we are done with this problem. I'll like to point out a few things over here before we go ahead. So this I told you earlier also, since gate current is very low, nanoamps or tens of nanoamps, so it's a very good assumption to make that Id equal to Is, which is I kind of derived here using the KCL. So just try to keep this in the back of your mind that you can always ignore the gate current. You cannot always ignore the base current in BJTs. So that's one advantage that we have here. And the second thing is that we just simply applied Ohm's law. Since Id was equal to Is, we just applied Ohm's law across this and this, and we solved the problem. And also one more point, we saw that Id was some finite current, it was not 0, Id was 2 milliamps. So this means that the device was not pinched off. So always try to just keep these things in the back of your mind when you're talking about FETs, whether the current is finite or not. Is it in microamps? Then if it's in microamps or lower, this means the device is most likely turned off. But if it's in milliamps, this means the device is conducting, it's not pinched off. These are just conditions because sometimes theoretical problems also come, that the current is low, is the device pinched off or not. So just these numerical problems help serve you build your theory also. So that was the point I was trying to get across. Okay, so I'm done with we are done with one more problem of FETs, and this is the reference that you can go. So in all of my videos, in all of the videos in fact which are being prepared or shown to you in the live sessions, so there is always a reference. So I also refer to these videos for better understanding of the concepts. And you might want to visit these videos. These are NPTEL course videos. Okay, so now any comments, any questions for now? Just please go ahead and ask. Okay, so now I have one last problem from the FETs itself, and this will be a last problem from the physics papers. After that, we have one more doubt from last week regarding digital to analog conversion. But first, let's look at this final FET video. I'm going to share my screen now. Okay. Um, are you able to see my screen? Yes, no?
Yes, sir.
Okay, so I'll play. The problem statement from Gate Physics 2018 reads as follows. An N-channel FET having gate source switch off voltage VG off equal to minus 2 volts is used to invert a 0 to 5 volts square wave signal as shown. So you can see the input over here. This is square pulse, and the output is just an inverted signal for this. So this is the JFET that the question is talking about. Now the question asks the maximum allowed voltage value of R would be. So this is the resistor we are talking about over here. The maximum allowed value of R would be dash kilo ohms. So we need to find the value of this resistor R in kilo ohms. And since this is a numerical answer type question, we'll round it off 2 decimal places and fill in the blank over here. Note the units is kilo ohms. Now that we have seen that the working of a JFET, and we'll try to use that information to solve this question. This is the question that is given to us. Note that what this question is doing, it's inverting this. So it's low. When the input is low, the output is high, and vice versa. When the input is high, the output is low. So what's happening is that this is the diagram that we saw earlier. So here you see this means that this JFET is operating in this ohmic region. So this is where it's operated in order to this is just an inverter function. So it's the JFET is operating in this region. So it goes from pinch off to saturation. So it's operating somewhere in this blue regime that we see over here, and it's behaving as a switch. So sometimes it's also known as switch or inverter. It's the same thing that we're talking about, and this is the region that we are interested in over here. Right, so this was the problem. VGS of is minus 2 volts, and this is I have just reproduced the diagram over here. And let's just first case about the case 1 when V in is 0 volts. Note that when the input is low and the output is high, and we'll try to figure out the value of R over here, right? And let's just put in all the currents over here. So as always, we assume that IG equal to 0. We assume that no gate current is there. So if no gate current is there, so we can simply say that ID equal to IS. Right, so that's a very fair assumption, because so let me do this. Step one is KCL across NJFET. So I can write IG plus ID, that's the inflowing current. It should be equal to outflowing current. Since IG is 0, this will give me ID equal to IS. So the drain current is nothing but the source current. Right, let's also now label some nodes. So this is the drain, this is the source, and this is the gate. I've just labeled it for easier understanding. Now what we'll try to do is that now we'll first try to figure out that whether this JFET is conducting is working or not, or it's pinched off. So how to do this? So that's step 2. So what we'll do here is that I'll try to find out the ID, because I know the output voltage here. So what I do is, step 2 is I'll apply Ohm's law across RD. So I'm calling this resistor as RD. Okay, so let's do that. So that will be 5 minus VD is equal to ID times 5K. So ID from here will come out to be 5 minus VD is 0. Note, VD is nothing but V out over here, and this is 5. So this will be 5 minus 5 over 5K. So ID is coming out to be 0 milliamps. So what this means is that this device is pinched off. and we saw that over here. So this means this device is operating somewhere in this region, right? And we know, so we'll write this is pinched off, right? So what does the pinch off condition mean? So that's our step 3. So pinch off condition means that VGS is less than VGS off, right? So this implies VGS is less than minus 2 volts. So we have obtained this condition. Now we just need to find what's the value of VGS, and note that VS will be equal to 0. So since ID is 0, note that ID is 0, so IS will also come out to be 0, and so no voltage will drop across this resistor, so VS will also come out to be 0 volts, right? So we just need to find out the value of VG over here, and that we can do very easily, since this is nothing but a potential divider over here. So I can directly write the expression, but let's derive it. So what I'll do is I'll apply Ohm's law across. So I'll equate the current through this as well as this. So let's do that. So the current will be flowing in this direction, so I'll write 0 minus VG over R. That's the current flowing through this resistor, and all the current will flow here because IG is 0, no current is flowing here. So this will be equal to VG minus 12 over 1K, right? So this is the expression that we have obtained, and let's just try to solve it. So this will be minus VG over R. So I'll assume R is in kilo ohm, so I'll drop this K over here. So this will be VG plus 12. So so this will give me that VG. So VG, if I take towards that side, it will be minus 12R over 1 plus R. Now we know that VG should be less than minus 2 volts, right? VGS should be less than minus 2 volts. We have obtained that. This means VG minus VS, which is equal to minus 12R over 1 plus R, should be less than minus 2, right? So if we try to solve this, this will be 6R greater than 1 plus R, and this will give me R should be greater than equal to 0.2 kilo ohms. So this is the first condition that we have obtained, that R should be greater than 0.2 kilo ohms. So this is the first half of the problem. We have just solved the case 1. Now we'll go ahead and solve the case 2, because we are not yet completed the condition related to R whatever we had. So now we'll just just to summarize, we had the KCL and the Ohm's law, so nothing special, and we arrived that we are in pinch off condition since the drain current was coming out to be 0. So that's how we knew that we are in the pinch off condition, and I just went ahead and solved the problem because we knew that we were in the pinch off condition. So that's how I did. That's how we obtained this inequality. The source of this inequality is this, that we know that the device is pinched off, right? So now what we'll go to the next. Now let's consider the second case when V in is high, that's 5 volts, and V out is 0, and again we'll try to find out the value of R. And so these are the current flowings over here. IG is 0, assume that no current is flowing, and so consequently ID will be equal to IS. We just saw that, so I'm writing it again, ID equal to IS. We know this information, and also let's label the nodes here. Now again I'll try to find the current that is ID over here, right? So I'll write, so this is the step 1, ID equal to IS. We saw KCL in JFET gave us ID equal to IS. So step 2 is Ohm's law across RD, that is the 5 kilo ohm resistor. This is what I'm calling RD, this resistor. Right, so let's do that. So it will be 5 minus V out. This should be equal to ID times 5K, and this will give me ID equal to 5 minus 0 over 5K, which is nothing but 1 milliamps. Now this is important. Now we do notice that some finite current, non-zero current is flowing through this FET. This means this FET is not in pinched off condition. So we see that this means this FET is somewhere operating in this blue regime, right? So it's not in pinch off condition. So this means I can write FET is not pinched off. This is important, not pinched off. This means VGS is greater than equal to minus 2 volts, because this is the VGS off condition. This was given to us, right? So now we will just simply find out what is the value of VG. VS is again will be very small, so we can ignore VS and we'll assume it to be 0. Note that since all the voltage is being dropped across here, so we'll simply assume that nothing. So this is again grounded. Note that this is grounded, right? So if this is grounded and this is minus 12 volts, so if this is grounded, then there's the very small potential drop we can assume. We are operating, you can assume, very near to this vertical edge, somewhere over here. The VGS is minus 2 volts, so, and this implies since VS is 0, VG should be greater than minus 2 volts. So this is the condition that we have over here. Now step 3, what we'll do is Ohm's law across R and 1K. So note that since no current is flowing here, the current flowing in this resistor should be equal to the current flowing in this resistor. So I'll write that. That will be 5 minus VG over R. This should be equal to VG minus 12 over 1K. So again, I'll assume that since in the units of kilo ohms, so I'll drop this K over here. So this will be 5 minus Vg over R equal to Vg plus 12. And if I rearrange some terms here, then I'll get Vg. The Vg I can write as, Vg can be written as 5 minus 12R over 1 plus R. This is the value of Vg, and we know that this 5 minus 12R over 1 plus R should be greater than minus 2 volts. So if I try to solve it, this I'll get 5 minus 12R should be greater than minus 2R. So this will give me 10R should be less than 7. This implies R should be less than 0.7 kilo ohms. So we have obtained that R should be less than 0.7 kilo ohms. And in the previous slide we saw that R should be greater than 0.2 kilo ohms. So this means the value of R should be greater than 0.2 kilo ohms and should be less than 0.7 kilo ohms. You can also put an equality here because we are operating at the near boundary. So for analysis it won't matter much. The question had asked the maximum allowed value of R. So maximum allowed value of R is 0.7 kilo ohms. So I'll write here 0.7. So 2 decimal places, I'll write it as 0.70 to make 2 decimal places. And that is the answer that we were required to obtain. Note, you can again put inequality choice. See note that we had here inequality over here. So you might as well do it greater than equal to minus 2 because we're operating near the boundary condition. So hence I put this equality also over here. So the answer is 0.7 kilo ohms.
Right, we are done with the problem now, but I have a few comments. The first thing is that since there were two conditions, when the input is low and the output is high, we solved the first case and we obtained an inequality. We got this condition, R should be greater than equal to 0.2 kilo ohms. Then we solve the other condition when the input is high and the output is low, and we got that the value of R should be less than 0.7 kilo ohms. So if you notice that the question itself said that this is nothing but an inverter. We saw NOT gate earlier also, right? When we're talking about logic gates, we saw that there are inverters. So this is an actual, this is a circuit or how an actual NOT gate is implemented. So we saw here. So it has many components and FET, power supplies, resistors, input and output and whatnot. So I just wanted to although we put in gates like there are some simple devices, they are not. This is just a NOT gate, and it's this much complicated. It's not a very good NOT gate. Remember, we had assumed that source voltage is 0. It's actually not 0. So when we take that, so this value will not be 5. This will be slightly lower. So there are some non-idealities, but as far as this problem is concerned, we obtained the answer from the two cases. Now you may say that we did not require to solve the first case. I know we did not require to solve the first case, but just you are here, we are here to understand how to solve the problem, not just solve one problem, but to solve every problem just by the same concepts. So yeah, that is all from me. We are done with the questions that we were required to do as far as gate physics session is concerned. So if you have any comments, any questions regarding FETs, BJTs, or any other thing for that matter, you feel free to go ahead and ask, because we are now done with the gate physics questions. So
Sir, are there any MOSFET questions in the gate physics?
no. As far as previous year paper is concerned, there were none. I tried looking for them again in the last 10 years. In the last 2012 to 2022, there are zero questions from MOSFETs. Good that you bring it up. A MOSFET is again an FET. It's a bit, it has four terminals rather than three terminals, so that's what difference. And also the advantage is that it's easier to construct, and it's very small. So in fact, that's how, if you remember, like I don't know if you remember, 20 or 30 20 years ago, the television sets and the computers used to be very bulky. They used to be very fat behind. Now they're not. The electronics has shrunk, and MOSFETs have played a very important role in them. And that's how you get better speed. So like mobile phones, smartphones 5 years earlier, even though they are less costly, now they are faster, right? That's happening because of the MOSFET. So we can pack more MOSFETs in the same areas, hence the performance becomes better. But unfortunately, there were no MOSFET questions. The MOSFET operating principle is slightly different than BJT and FET, than JFET, junction FETs. It's slightly different. It's a metal oxide semiconductor field effect transistors. So I don't know whether they'll come in the next year or not, but I could not cover them due to the lack of time. So that's about that. Yeah. Any other comments?
Sir, can we make
One second. Pratik, go ahead.
Sir, can we make a diode forward bias using a constant current source?
So see, the diode requires primarily that the PN junction that you have, that the primarily the PN junction that you have, it should be forward biased. That's the idea. The voltage to the P junction has to be positive, as has to be higher as compared to the N junction. So that is what we mean by forward bias. Now I'll have to see what the source current is, because if it's an ideal current source, then depends on how much current is being injected. There are some, I mean, it's not a straightforward question that I can give you an answer right away. That's my thing. You can email me that question and we can talk. Just
Okay,
email
thank
me
you,
that.
sir.
Yeah. Aishwarya?
So, what is switch off voltage?
Sorry, I could not understand. Please repeat.
What is switch off voltage? We have seen in the last question.
Okay.
VGS off.
I'll try to talk about it. Just let me share my screen now. I hope you can see my screen, right?
Yes, sir.
Yeah. So you see this. This is in the question we had talked about this. So here on the extreme left, you have the junction FET. You can see this in this dashed region. This is a depletion layer. However, if we apply some negative bias, so I'm making gate is, remember, P type, and if we apply negative bias with respect to N type, so this junction becomes reverse bias. This PN junction becomes reverse bias. And when a PN junction becomes reverse bias, its depletion width increases. Note that depletion width is narrow here. It has increased here, right? So it has increased, but you can still see that this channel is free. So electrons can flow in this direction, right? Electrons can flow into this. However, if I apply more negative bias, this means this region will push to this side and this region will push to the left. So let me just use my pen now for better understanding. So if I apply more negative bias, so what will happen is that this region will push towards this side. Similarly, this region will push towards this side. And that is the case here. If I increase the negative bias, these two depletion regions merged. Now current cannot flow. Current needs a channel. See, a better way of understanding is, you need a highway, you need a road to drive a motorbike or a car. This is the road. What's happening is that there is some encroachment happening from both sides. This is the depletion, is the encroachment. This is the footpath, you can say. So the footpath covers the entire road. You cannot drive a car or bike or a scooter on a footpath. So no cars can be driven, means no electrons. The analogy is no electrons can flow, and thus no current. That is what we mean by pinch off. Note that this is being pinched off, like when you touch your finger and your thumb, and nothing can flow in between. So that's the reason that's happened. So, look at this as the first finger and this as the second finger, and nothing can flow in between. Sorry, my drawing is a bit bad. So nothing can flow. There's no path for electrons to flow between drain and source. Hence, there's no channel, there is no current. Hence, it is VGS off. The voltage at which these two depletion regions touch, the gate bias at which these two depletion regions touch, is known as VGS off, or the pinch off voltage, which is being shown like this here. Did I explain what your doubt was, Shwarya?
Yes, sir.
Okay.
I got it.
Okay. So we have one more thing to do from the last class before we finish. We still have 2 or 3 minutes. Okay. So yeah, this. So who asked? I have forgot. Sorry. Who asked me to cover digital to analog converters? Are they here? Prateek, Aishwarya, and Priyanka. I think you 3 people are here right now, if I'm not wrong. Did anyone of you?
Sir, I asked about this doubt.
Okay, very good. You are here then. So yeah. So remember, in operational amplifier we have solved one problem in which we had an adder circuit. I cannot. This was the circuit. So you saw that the negative feedback, and these were in that question there were just 2 resistors here, V in 1 and V in 2, and there is this feedback resistor here. And we simply solve this circuit. You simply apply the KCL over here. So all the current that is flowing through these 4 has to flow like this, like the simple KCL and KVL we used to do. It's just very simple, just like that. So just to answer your question in very simple words, how does a digital to analog converter implemented? It's implemented using an operational amplifier in negative feedback mode with some resistors, and these are the digital inputs: V in 1, V in 2, V in 3, V in 4. You see these 4, these are the bits. So this is bit 1, bit 2, bit 3, bit 4. What I mean to say is this. So this is again a very simplified version. This is an operational amplifier. So with a negative feedback, you see the feedback is connected to the negative terminal here, and these are the 3 bits. So this is the first bit, the LSB, least significant bit, what we call LSB, right? And this is the MSB over here. This is the MSB over here. So what we can do essentially is that we can apply the KCL over here, right? So note that, remember the virtual short condition we talked about. So this node will always be at 0 volts. Will also be at 0 volts because the positive terminal, the non-inverting terminal, is at 0 volts. So inverting terminal will also be at 0 volts. Now you can simply apply the KCL which we used to write, like V2 minus 0. So it will be V2 minus 0 over R. That's the current flowing through this. Let's call this I2. So this is I2 plus the current I1 would be here. So current I1 would be V1 minus 0. I'm writing this here. V1 minus 0 over 2R. That's 2R. Sorry, 2R. Finally plus. Let's assume this current to be I0. Right, I0. So this will be V0 minus 0 over 4R. This is the current flowing in. So all this current will flow over here, right? So what is the current flowing out? So the current flowing in this direction would be 0 minus V out over R. So what happens is that if you solve this circuit, you rearrange these terms, so you can calculate V out in terms of V0, V1 and V2. So this was the circuit, and this is the formula that you get. So I have just rearranged those terms. So you get this formula, V out equal to minus R, and you cancel the resistor values. So you get V out equal to minus 1 by 4, 4V2 plus 2V1 plus V0. This is nothing but an adder or summing amplifier. We had talked about this earlier, right? So now what I'll do, and I also told you these are nothing but the bits, right? The digital bits that we had, the first bit, the second bit, and the third bit, and so on. So I write this V0, V1 and V2. Note that this is the digital value. So this is 0, 0, 0. This is 0, 0, 1. You can see this 0, 0, 1, 0, 1, 0, 0, 1, 1, and so on. This is the digital value, or you can say the decimal value over here. And you put V0, V1, V2, these values over in this formula, and you can get the corresponding V out. You can get the corresponding V out over here. So you see for this is 0, and you can see these are the analog values, right? Now you will argue these are not analog, they have a finite gap of 0.25 volts. You can get finer tuning also, but note that this is just a 3-bit converter, right? If you go to 8 bits, the resolution will improve. Note that we have also talked about resolution in ADC, analog to digital converter. Similarly, there is a resolution term here also. But this is the basic idea. The more bits you have, the better the resolution you can have. Now the resolution is 0.25 volts, right? If let's say you had 5 bits or 8 bits, the resolution would be better, maybe 100 millivolts or even less. So we have in the market digital to analog converters with resolution of a few microvolts also. So then they have a large amount of digital inputs. The bits are high, so that's the way to go. But I just wanted to introduce you to the idea and clarify about how it's implemented. So it's implemented using an operational amplifier in a negative feedback mode with some resistors. These are often called R2R circuits also. So you might want to look it up on the NPTEL videos or some textbooks that you have. So these are R2R circuits with operational amplifier. It's very straightforward, like I did some analysis over here for you, right? So it's a very straightforward thing to implement and to understand. So yeah. So did I answer your doubt, Priyanka?
Yes, sir.
Okay. So any other comments you have? Any other follow-up questions?
Sir, can you explain about the metal and P-type semiconductor junction?
Okay, I'll try to do that because I need the slides for them. Let me just look it up for a minute and I'll try to do that. Okay, just hold on. So in effect, the P-type metal semiconductor, the P semiconductor junction and the metal junction behave more or less like what we saw in the N semiconductor junction, right? It's just that the Fermi level is at a different area. That's the only difference that I can say will arise. So what I'll try to do, I'll try to figure out where we have. I found one figure. So yeah, so let me open it and then I'll share the tab. Okay. So right, can you see something on your screen now? Anyone?
Yes, sir.
Yeah.
Yes, sir.
Yeah, so on the left, what we had talked about was metal and semiconductor. So you see, if you remember, we saw this kind of a trend like this, right? So this was the Schottky barrier, and so what's happening is that a similar thing is happening here. Now notice that. So in this case, the Fermi levels, the only thing that you have to make sure is that in equilibrium, the Fermi level has to be constant. So in case of N semiconductor, since the conduction band has to be close to the equilibrium Fermi level. So what I did, you first draw the equilibrium Fermi level like this here, and then what you try to do, in the bulk, the valence band has to be close to Fermi level since it's a p-type semiconductor, and then you simply bend the bends. So because it has to be here, the initial point has to be here, so we were required to do that. So bending of the bends happens at and where it's aligned earlier. So that is the thing that's of vital importance here. So the direction will be reversed, but the physics, the basic idea that we have does not change in N semiconductor or P semiconductor. So yeah, that's that. So the key thing, I repeat, is to remember that the Fermi level in equilibrium has to be constant. And second thing, in bulk, for P semiconductor, the Fermi level, the valence band has to be drawn close to the Fermi level because it's a p-type semiconductor, and accordingly the bends will bend. So in this case, the bends will bend like this, and this is the barrier that you see over here. I should also clarify that it also depends on the work function. So here the work function is like this. So here the semiconductor work function is higher as compared to the metal work function, while it was the inverse case here. So yeah, there are 3 or 4 different cases. Just write to me on my email address, and I'll share you a bit more details. Is that fine, Priyanka? Will that be fine?
Yes, sir.
Okay, I'll share my email address again over here. So if you have any doubts, please feel free to contact me. Yeah, I've shared it in the chat box, so you can just make a reference to that. Yeah, and that's it. Any other doubts, Priyanka? Just write to me, so otherwise I might forget. So please write. It's a very simple. It's a very simple. There are 4 images in that. In the 4 diagrams in that image, one image which illustrates the p-type and n-type semiconductor junctions with metals. It's very simple to understand, and you can also see the differences between n semiconductor, p semiconductor, and metal junctions. So I'll share that with you, right? I don't have it ready with me. It's in a book. I have to search for that book and then send you the picture. Okay, but I'll do that. Okay, any other comments, people?
Sir, in the J-type FET, if the gate to source voltage will be positive, then there will be no current.
If we are talking about gate to source voltage, no, the current, see, gate to source voltage is the gate bias determines how wide will be the road, right? We just saw that if we increase the negative gate bias, the road closes, right? The depletion region increases and the channel in which the electrons can flow gets reduced. So if we apply positive gate bias, let's say you increase up VG, so that would mean that the channel will be, I'll again share that slide with you, and I'll just hold on a minute. Let me search for that. Yeah, I found it. So I'll share it with you. Just give me a moment. Yeah, so what's going to happen is that, so let's say this is the original case. Okay, I'll not confuse you. So this was the case that we had here, right? So this is unbiased. Now what you're saying that you want to apply a positive VGS, right? That's what you're asking. Let's say VGS equal to 1 volts. So what will happen? What will happen is that, so I'll draw this fellow over here. So this is the p-type, this is the gate that we have, right? And this is the other gate that we have, and the depletion region, since now p-type you are saying it's forward bias, it's 1 volts. This is the source, this is the source, this is the gate. So if VGS equal to 1 volts, right? If VGS has been set to be 1 volts, now what's going to happen is that the p-type, this is a PN junction, and P is connected to higher voltage as compared to N. This means this is forward bias, so depletion region will become very narrow. I'll use a different color to illustrate that. So depletion region will become even narrower. So it was this here, it will become very narrow now. So what that means is that this channel, the channel which I'll now denote in green, so this channel width has increased, right? Let's say this channel width was 1 micron here in unbiased case. Now let's say it has become 1.2 microns. So if the channel width has increased, now more electrons can flow. So here is source and here was the drain. So if you apply positive bias to gate source, effectively the channel width increases, and more electrons can now flow when you apply a drain to source bias. So yeah, that's that. But it does improve, yes. You are asking what does it improve? It does improve, yes. The current improves, correct. Does that answer your question, Priyanka?
Yes, I was asking about that there will be current or no current if positive bias will be there.
See, if you have VGS equal to 1 volts and you are saying drain equal to 0, because I can only comment on the current when the current flow happens due to the drain to source bias. So as I was telling you, gate to source determines the width of the channel. The amount of current is being determined by drain to source. So since now source is at, let's say, so VG equal to 1 volts. Now this is VG. So VG is now you are saying 1 volts. Now there is also one more voltage source here. So you have to tell me what is the bias applied here. Then only I can comment whether the current will flow or not. Current flow will depend whether there is bias between VDS or not, right? So that is the other. So note that there are 3 junctions. So gate will determine how much current will flow, but you have to apply a bias. So tell me what is the bias, and then I can comment. So let's say even if you apply a VDS equal to 0.2 volts, then yes, a current will flow. Current will definitely flow. So the other way of seeing it is this. We saw this diagram. This is VGS equal to 0. This is VGS equal to minus 1 volts. This is VGS equal to minus 1. And here somewhere over here would be VGS equal to 1 volts. VGS equal to 1 volts, and over here would be VGS equal to 2 volts. So current will flow, yes, provided you apply some VDS. Note that if VDS equal to 0, no current can flow, whatever you may do. However high VGS you apply, you have to apply some VDS to get some current. So that's the idea. So current will flow, provided you apply a VDS. Now did I answer your question, Priyanka?
Yes, sir.
Okay, good. That's satisfactory for me. Right, any other comments? Priyanka, Aishwarya, Pratik, thank you for sticking around. Thank you for the 12 weeks. I think you are one of the
Thank you, sir.
Okay, good night, stay safe, bye bye. If there are no other comments, we'll close this session. If there are any comments, please speak. All right,
Thank you, sir.
thank you everyone. Good night.
Good night, sir.